All right, good afternoon, everyone. It is officially afternoon, unfortunately. Welcome to Where Should I Be Encrypting My Data? My name is Denny Cherry, Principal Consultant for Denny Cherry and Associates Consulting. So if you'll bear with me for 10 seconds, I'll talk about myself and then talk about the stuff you guys actually came here to listen to. I've written a whole bunch of books. It's actually more than 6 now. I think I'm actually up to 9 books now, including the Securing SQL Server book that this session actually ended up coming from. That's actually come out in 3 editions, and unfortunately it's a little bit old at this point, but the publishers don't want to give me the rights to make a 4th one, so blame them that I can't update it. I've written dozens of articles for various websites, including WinIT Pro, MSDN Magazine, back when SQL Server Magazine was still a thing. I wrote for that as well as a bunch of other various places. I've been a Microsoft MVP for, I believe, 16 years now. I've also been a VMware vExpert for 6 years in that program as well. I'm also one of the very few Microsoft Certified Masters, and of all the people that are both Microsoft Certified Masters and Microsoft MVPs, I believe there are 4 at this point, and of those, I'm obviously one of them because I hold both of those. I've also been an EMC elect, and I'm currently a Microsoft Certified Trainer, I believe, until the end of next month. So, the things I want to talk about today, I want to talk about a quick overview of encryption versus hashing and what the differences between those two things are and when they should be used in the various databases and in the various applications. I want to talk about data encryption and where all the places are that you can encrypt data within your application. And then I want to talk about a few myths that are out there that I've seen and heard about encryption when talking to people and talking about clients. So first, the interactive portion of the exercise. Who is running SQL Server 2022 in production? Absolutely nobody. One person, iffy. Okay, 2019, we're going all the way back as far as we need to. About 3/4 of the room. Okay, so that was 22, 19. So next is 17. 3, 4, 5 people. Okay, 16. Same people. Not surprising because they're the same engine. 14. 2, 3, 4, 5. 4 brave souls. Okay, 12. 2 brave souls. Okay, I'm so sorry. So we were on 12, so 2008 are 2. One sad soul left, 2008. No, I'm so sorry. What's before 2008? 2005. Oh, God help you. That one of them left. Okay, can't get rid of it. Okay, so 2000. Okay, and we're done. All right, thank God for that. I have actually at this conference, a couple of years ago, we went all the way back to 6.5, some poor soul. And it was not long before the pandemic that he still had 6.5 in his enterprise, that poor guy. And sadly, he probably still has it for some stupid regulatory reason. So these are 2 ways that I like to explain the difference between encryption and hashing. The idea being, with encryption, I can get the data back out. So on the left, on your left, we have a black and tan. So if we try really hard, for the most part, we can separate that back out and get the base ingredients out of that. On the right, we have a vodka cranberry. Yum. We'll probably find some of those later this week. Those you are not getting the basic ingredients back out of. You cannot separate that no matter how hard you try or how many of those you drink. You are not getting those back to the cranberry and vodka that they were. And that's the basic idea. With encryption, we want to be able to get back the original value. With hashing, we only care about the hashed value. So you'll hear about this a lot in password breaches from Troy Hunt and stuff like that, where he'll talk about the fact that they had their data hashed versus their data encrypted. Hashed data is really good for things like passwords, because I don't care about the actual value. All I care about storing is the hash. When a user enters in, whatever their password is, so they enter in their password of password 123, or 12345, maybe they're a Spaceballs fan. I saw it recently on a plane. They'll enter in that number. It'll go into the app. The app will then hash it and compare that hash to the hash that's stored in the database. The reason we do this is because we don't care about getting the data back out. There's no need to. There's no possible reason for us to need the original value. All we care about storing is that hash. Whereas with encryption, we'll use this for data that we do want to get back out. So maybe we're storing in the database the user's tax ID, the customer's tax ID. So we'll want to get that tax ID back out because we need to use it somewhere in the application. So we either need to display it to a customer service rep, or we need to be able to run a report and get that data and send it off to the government saying, hey, these tax IDs have gotten these loans or something like that. So we'll need to be able to get that data back out. So we need a two-way process. So we'll use encryption to make sure that we can get that data back out of the application so that we can then run reports or do whatever it is that we need to do on it. So, like I said, encryption is going to be a two-way process. We can send the data in, we can pull the data back out. The values should be what we call salted to make the decryption of the value harder. So what I mean by that is when we put a value into an encryption algorithm, there's a second value we're going to put in as well, and that's going to be the salt. The salting value is going to be effectively a static value, either for the entire application or just for that user, so that we can always make sure that the data that's being encrypted is always being encrypted differently for every single time. So if we change the salt value, that changes the way the data is actually stored in the system. When you decrypt it, you don't necessarily need the salting value, depending on what encryption algorithm you're using. But because we're basically making that encryption harder to decrypt, we're making the data safer. If we use the same encryption algorithms with the same data with no salt, we're going to get the same value every single time. By changing the salting value, we're going to change the data that's being stored in the system, and it's going to make that decryption much, much harder. Now, the downside for database administrators. So actually, before I go on, who are my database admins in the room? About half the room's database developers. Yeah, basically the rest of the folks, sysadmins. Okay, a couple of people. People who are just looking for free lunch. Three. Well, yeah, but I know you, so. Mutually exclusive now, yeah. So the problem with encrypted data is we cannot index it in the SQL Server. So we see this in always encrypted in modern versions of SQL Server. I'm so sorry, this is available in SQL 2005. You are not going to be able to effectively encrypt your data with really any encryption process, especially if you salt it. The reason for that is to index the data, we would need to be able to decrypt the data to actually do the lookup. And obviously that is not going to be a very well-performing process if we need to decrypt everything in the table to try to get the value out of the system. The strongest encryption that's out there is effectively unbreakable. The reason I say effectively is because there ain't no guarantees, and Azure is really big, and I can throw a lot of CPUs at the problem. And so eventually, if I spend enough time and I put enough compute behind a forced decryption process, it will eventually decrypt the data. But CPUs in Azure are not free. So this is the trade-off. Yes, I can throw 1 billion CPUs at the problem and eventually decrypt your data, but somebody's got to pay for that, and somebody's going to notice that I'm doing that if I'm using like a stolen credit card number or something like that to try to buy all these CPUs. Somebody's going to notice a 100 million pound charge on their credit card, I would hope, is going to show up. When you're doing things like encryption in SQL Server, AES 256 is the encryption algorithm we typically want to use, or even something stronger than that. As of, I want to say, SQL 2016, 2017, AES 256 is going to be as strong as supported. I think the newer versions actually do support some what we call AES 512, which is a slightly stronger algorithm. It's going to give you more encryption, a better encryption process. So with hashing, like I said, it's going to be a one-way process. Because it's a one-way process, you can index it because it's going to be getting the same value every single time when you hash it. So say I've got a table of hashed values stored in my database. So, all these various binary values. When I I can index that column. When I then hash the value that's come in from my application, I can then simply do a compare. So I can do your standard bookmark lookup and get back the hashed value nice, or the hash row nice and quickly and see if there's a match. Back in the day, we would recommend MD5 or SHA1, or what we call SHA1. Now, actually, those have both been deprecated because there have been weaknesses found in those algorithms, and I need to update this slide. So we would actually use a newer algorithm than SHA1 and MD5 to actually do your hashing, in SQL Server. So we have what was called SHA-3, which is that new, stronger version of the SHA or the SHA algorithm. That's going to give you that better version of hashing. It's going to give you a safer, more secure process when it comes to hashing. My start menu is not going to be helpful on my screen. So salted hashes, unfortunately, are actually not supported in SQL Server by default. So there are a couple of ways to get around this problem. The easiest way is to take a value, the value that the user has inputted, and simply append an additional value, your salt, onto the back of that, and then hash that. The main reason that you want salting values in your hashed algorithms is so that what's called a dictionary attack or a dictionary lookup can't be done. So if I don't use a salted value, and I just do, let's say, an MD5 hash of the word password, I can literally take that string, go online to a online hashing dictionary, pop in that binary string, and it's going to give me back all the values that match that string, including the word password. So it's going to give me back all the various values. Now, if I've salted that, that's not going to work, especially if I use a really long salting value. So one of the ways that you know that a website isn't using any sort of salt or really any sort of hashing at all is if they've got a really short password length requirement. So maybe they say, you can only have a password between 4 and 8 characters on our site. Well, that's horrible. And we know that that means that they're putting those 8 characters into a database table. We all know databases. And they're not encrypting it. Because if they were they're not hashing it. Because if they were hashing it, we wouldn't care how long the value was. A hash will always be the same length. If I hash the letter A, or if I hash whatever the longest German word is, I pick on them because they have the longest words, they're both going to come out with the same length hash. If it's an MD5 hash or a SHA-1 hash, it's going to be 64 bytes in length. Every time, guaranteed. Doesn't matter what we pass in. So in 8-character password, if they've got that stupid requirement, they're not hashing the password. They've done something really dumb at the application level as well. So, like I said, so you can either pass this in and just append a value. You can write a custom function in SQL Server to do the hashing. Well, basically, it's going to append that value for you. So the process when the user passes in data, or when something needs to be hashed from the application, we're basically going to hash the passed-in value. We're going to combine the hash with the salt, and then we're going to hash that value again. That's another way of doing this whole salting process. Whatever the process is, as long as you're doing the same thing every single time, you're going to get nice hashed values that you can shove in SQL Server and you can store somewhere, and then you can do lookups against those. Encryption is almost always going to, usually rather dramatically, increase the size of the data being stored. This is one of the things you're going to need to remember, especially if you've got an extremely long table. This is, your standard problem. Well, in dev, I only needed 3K to actually store this data, where in production, I needed 200 gigs. This is one of those places where this is going to be, going to really show up for you. When you encrypt a value, it's going to get significantly longer just because the encryption process is going to throw a lot of garbage data in there to make the data look encrypted or to make the data be encrypted. It's going to radically decrease the usefulness of any data duplication within your database. So I had a customer years ago where they were getting something like 70% dedupe on their storage array for their data file, their MDF file. As soon as we turned on encryption on a couple of their main tables, their dedupe process on their array dropped to like 10%. And the reason for that, every value is different now. Even if the values are actually the same, because they're now encrypted, the values are actually different. The thing to also remember about data encryption, when you put it into an application, it's got a CPU cost. It's just a matter of where you're going to spend that CPU power, the CPU time. Are you burning it on the SQL server? Are you burning it on the app server or the web server? Or are you burning it on the client? All that matters, all that's going to really depend is where am I going to burn it? Because I'm spending it somewhere. Something has to actually do the encryption, and encryption is not free. It's not. You have to encrypt the data. That takes CPU cycles. It requires lots and lots of math to do it. So, because of this encryption process, something has to change. Some code has to change. The exception to that rule is always encrypted. With always encrypted, we don't necessarily have to change code. That's the beauty of always encrypted. Everything else, something is going to have to change because something has to do the encryption and the decryption. So we have to tell the app, hey, you take this value and encrypt it. So we either need to write changes to the .NET code that's running the application, or we need to make changes to the stored procedure that's being called that's doing the actual work. So something has to change. Along with that, we're going to need to change the schema of the database. So say we're encrypting I'm going to use the US Social Security numbers because I know off the top of my head how long they are. It's a 9-character value with 2 dashes in it. It's always 9 characters. When I go and encrypt that value, however, now suddenly that 9-digit, which is probably char 9, it's now going to blow up to 30, 40, 50 bytes wide, depending on how I'm doing the encryption. So I'm going to need to make the change to my tables. I'm going to need to make the change to any variables that I'm using in stored procedures, any input parameters I'm using in stored procedures. And I'm going to need to change the application to handle the fact that there's this bigger value coming out and going back in. Not to mention the fact that we need to actually change the code to make the process actually happen. So the nice thing about encrypting values is the data is going to be actually encrypted within the database. So when a user comes into the database and they just do a select star from table, and they start looking at the table, all they're going to see is the encrypted values. They're not going to see any of the source data. And this is the whole point of encryption, is to make sure that users or people can't see data they're not supposed to actually see. That's why we do all this. So when we want to make those changes in the application layer, so this is when we're actually doing the encryption in the .NET layer itself, in the actual application, this is potentially going to require a rather lengthy rewrite of the application. We're going to need to change code. We're going to need to bring that encryption process in. We might need to store certificates somewhere to actually manage the keys for this encryption. This is going to require database change, database code change. The nice thing about doing the encryption in the application is we're spreading that CPU load out. All SQL Server knows is data is coming in that's been encrypted. The application, on the other hand, needs to make changes. So this is going to require a decent amount of app dev time because developers have to change code. Now, me personally, I'm not an app dev. I'm a DBA. I'm fine with this. It's not my problem. You go do this and tell me when it's done. That's all that has to happen for me. So my life gets relatively easy. Now, the reason that we have this thing called Always Encrypted, which was introduced back in SQL Server 2019, 27? Yeah, 2019, somewhere in there. I don't remember the version. So was it 16? There's way too many versions of the damn product at this point.
19 was secure enclaves.
That's right. That's where I'm going. Secure enclaves. With Always Encrypted, we were able to get away from a lot of these app rewrites. The goal, and they were relatively successful, as long as you didn't want great performance, with Always Encrypted, was you could literally flip it on, tell SQL Server, hey, we're doing Always Encrypted on these columns. We could store our certificate that's managing the keys for the encryption off in our Azure Key Vault or off in a third-party key management system. And we could do all of this without really any code change because the SQL Server driver was the one doing the actual work. And this is one of the great things about Always Encrypted. Now, it worked great unless you were in a really high-performance application, really high-performance shop. Then you would need to actually make some minor tweaks to the actual application code to get the extra performance that was possible out of Always Encrypted. But if you're in a regular company doing regular stuff, which most of us are, you could literally drop in Always Encrypted, change the columns to being encrypted with Always Encrypted, and you were done. You didn't need to really do anything else. We actually did this with one of our clients, I want to say 4 or 5 years ago now, and it worked beautifully. We literally just dropped it in, made the necessary database changes, and we didn't have to change the app at all. So the whole process worked absolutely flawlessly. So the other place you can do the encryption is within the database layer. So when we do the encryption at the database layer versus the application layer, the reason we'll do it here is because we don't want to or can't change the app, but we still want to encrypt the data. So SQL Server has a bunch of encryption options built into it, not just Always Encrypted, but some of the older stuff as well. So you can actually encrypt data as it comes in, you encrypt it within your stored procedures, you store it as an encrypted value, and then you simply decrypt it through the stored procedures and pass it back as clear text to the application. It's not quite as good as Always Encrypted, because with Always Encrypted, the data encryption is being done by the ODBC driver itself, whereas with this, it's being done by the SQL Server engine. So we're passing clear text from the database to the app, or to the website or whatever it is, and only doing that encryption and decryption on the database itself. Whereas with Always Encrypted, because we're doing it at the ODBC driver, all the data being passed from the app to the database is actually going to be encrypted from the beginning. So it does require some code change, but all that code change can be done in the database. Again, I'm a DBA, that's a developer problem, so I'm fine with that. The problem is going to be this bottom bullet point here. Centralizes all the encryption workload on the database server. Now it's a me problem, because I'm the DBA, I'm the one responsible for how much CPU those processors are chewing up. When we've thrown the CPU on those, or the CPU workload for the encryption on the actual SQL Server, we're now going to drive that CPU up, probably dramatically, depending on how many users you've got, depending on how many CPUs you've got. Now, back in the day, this was a big problem because we only had so many CPUs. Back in the day when I first started talking about encryption, when I first started dealing with this stuff, 8 CPU cores was all we would get in a box. That's all a server could have. Thankfully, you can throw a lot more CPUs at a server these days. In Azure, you can get SQL Server VMs that have, I think, 418 cores. That's a lot of CPU, but that comes with a cost. In this particular case, that cost is good old-fashioned money. Last I checked, the 417-core SQL Server costs something around $1.3 million US per month. So unless you want to go to your boss and explain why you need $1.7 million per month, we probably want to come up with a better solution than that. But there is a solution out there, and it is relatively easy to do and relatively easy to implement as long as we can deal with the fact that our CPUs are going to go up rather dramatically. So, encryption of data at rest. So those are both great options for moving data and storing data, and actually having encrypted data in the system, in the actual database. So when we would go query the tables, we would see encrypted data. We would see effectively useless data. What happens when management comes to us and goes, hey, we've got this compliance requirement that says that we have to store the data as encrypted values. I want to make this change. How long is it going to take? Well, if we're in Azure, it's easy. That's already done. If we're on-prem, I can do it in about 2 lines of SQL Server code, because all I can do is turn on what's called Transparent Data Encryption, or TDE. When I turn on TDE, it's going to encrypt the data as it stores it on the hard drive, decrypt it when I read it back from the hard drive. So I call TDE the checkbox requirement of SQL Server encryption, because all we're doing really is going, all right, yeah, check the box. We are storing encrypted data. We are not actually doing anything interesting with the data. There's a very small CPU overhead to do this. There's a very small I/O overhead to do this. But generally speaking, it's relatively easy to build into the system and just flip on. When people ask what the cost is for TDE, I'm going to say it's typically about 1/10 to 1/2 of 1% of your existing workload. So if your CPUs are running 20%, that's 1/2 of 1% of that 20%. So that's basically nothing. So there's really no reason to not flip it on. The one thing to keep in mind with TDE is it's going to, at least in the older versions of TDE, going to disable instant file initialization. It's also going to turn on TDE for the TempDB database. So if any database has TDE turned on, that's going to force TDE to be turned on for TempDB. If you turn off TDE on all the databases, when you restart SQL Server, it will automatically create TempDB without TDE turned on. The reason Microsoft does this is they don't want to run the risk of data being loaded from a user database table to a temporary table, and then have that temporary table stored on disk as an unencrypted value. So that's the whole reason they turn on TDE automatically for TempDB. So, backup encryption. Oh, I got one more bullet point I need to add to the slide that I forgot about. So there's a few ways to deal with backup encryption. The first one is with TDE, just simply by turning it on. Any database protected by TDE is going to have the backups automatically encrypted. The reason for this is because when the backup process runs, it does not decrypt the data. It simply takes the data page from the data file and copies it to the backup file. So backup data just streams from one file to another. So we don't decrypt the data. So you have to have the certificate that you used for TDE on the server when you restore the database. If the certificate's not there, the database will not restore, because SQL Server cannot read the file. Yes, sir?
Can you have multiple certificates on the server?
Yeah, go ahead.
From an audit perspective, we have requirements where an external auditor may come in and say, give me that database, restore that database from 4 years ago.
Right. So the question is, can you have multiple certificates on the same server? The answer to that is yes. So you can have multiple certificates. You can have one certificate for every database. If you've rotated your certificates, for example, and you want to keep the old ones on the server for some reason, so for the perfect example being your audit requirement of, hey, I want to restore this database from 4 years ago and see what it looked like, yes, you can do that. So you can keep all those old certs there. If you're dealing with old certs, I would recommend not actually keeping them on the server, but pulling them out of the database. So basically backup certificate to a file, and it'll drop the cert to a file. And then you can pull it off the database server. And then if you need to restore the database, you can just restore the cert, because then you'll probably want to take those certs and like burn them to a CD or something. We're talking like old school stuff here, because like on-prem CD drives, and like I don't even have a machine that can read a CD anymore. But you'll come into a thumb drive or a CD drive or something like that. God help you, a floppy drive. Does anybody remember floppy drives? Okay, there are a few of us that are old enough to remember floppy drives. For the young folks in the room, that's the save button. That's what they used to actually look like. I have an 18-year-old at home, and I want to kill him sometimes when he talks about stuff like that. But yeah, so you can put all those certs there. I say burn them to a CD. Actually, I say burn them to 2 CDs. Keep one in the IT manager's office. Give one to HR, because they have a fireproof safe in their office usually. So just shove the CD in there, and that way, if God forbid something were to happen to the building, odds are that CD will still be safe. Yes, sir.
So certificates expire after some time. If you have a database backup in cold storage for 5, 10 years, and you restore that with an old cert, is that even possible?
So the magical question of what happens when the certificate expires. So the beauty of TDE, and one of the best decisions the SQL Server team has ever made when dealing with TDE and setting it up, is TDE ignores expiration. So you can have a certificate for TDE that has been expired for 20 years, and it will be just fine. So you do not have to worry about what happened to that certificate that was, sorry, I moved my shirt and yanked on the microphone cable. So you do not have to worry about that old cert from 20 years ago or 10 years ago or whatever with your cold storage database. You will be able to restore the certificate and then restore the database on top of it, because SQL Server does completely ignore expiration dates for certificates for that exact reason. While it would be great if we didn't have expiration, or sorry, it would be great if SQL Server did follow expiration. There would be the downside of locking ourselves out of our backups after whatever the expiration period was, or God forbid, locking us out of our online database because the certificate expired. So obviously, to avoid those problems, Microsoft made the decision of simply ignoring the expiration. So there are third-party products that will do backup encryption as well. The newer versions of SQL Server will also do backup encryption, even of a non-encrypted database. So you can have a traditional non-encrypted database running and simply back that up to an encrypted values as well. If you're doing the native options, you can also push those backups straight to Azure Blob Storage as well. So you can still do all the new cool stuff, even while doing the traditional processes. If, God help you, you're using a managed backup solution like an Avamar or an IBM or something, one of those big honking tape backups in your data center, those will typically do some form of encryption as well of the backup as it's being written out to the tape. So we can encrypt data on the wire as it's transferring data from one server to another, so from the database server to the application server, using a process called IPsec. What this is going to let us do is simply protect any data in transit as it's going between machines. So basically the goal here is going to be that we don't trust our network administration team, and we want to make sure that they're not spying on the SQL Server traffic and decrypting that traffic. The other option besides IPsec is going to be to turn on SSL within the actual database engine. And conveniently, I should have slides on both of those. So IPsec is an international multi-platform standard. It's supported by Apple, by Linux, by Unix, by Microsoft, you name it, everybody supports it. What you do is basically turn on IPsec on both sides. It's easy to do in Windows because you can push out the settings through group policy. So they'll hit all the machines on the domain. And then all the traffic between various endpoints will then be encrypted so that nobody can actually sniff the traffic. Obviously, the data stored in the database is still going to be unencrypted. The application wears zero change because all we're doing is telling the machines, hey, as machine A is talking to SQL Server A, encrypt that traffic. Traffic between machine A and machine B, unencrypted. So we can specify exactly which traffic we want to have encrypted throughout that process. This is potentially going to increase CPU load on the servers. It might not, however. Most network cards, or at least most modern network cards, are going to have what's called an IPsec offload engine built onto them. It's basically a small chip built onto the network card that will handle all the IPsec for you. And things like the Windows operating system know that this chip is there, and they will send all the IPsec configuration to these cards. And so the network cards will then do all the work for you. So you won't actually see any increase on your SQL Server. If you don't have these specific cards or these specific chips, then obviously your CPU is going to go up because, again, something's got to be doing the encryption and something's got to be doing the decryption. So the other option we have, besides IPsec, because IPsec can be a pain to set up, is SQL Server over SSL. So this is the same SSL we're using for things like Amazon, for online e-commerce, and conveniently enough, for Azure SQL Database. So same exact process. A certificate is given to the SQL Server. SQL Server is told to use that certificate to encrypt all the traffic. SQL Server will then encrypt any traffic where the ODBC connection says encrypt the traffic. If you don't want to go changing all your ODBC connections on all your app servers, there's actually a checkbox you can check in SQL Server Configuration Manager that simply says configure all traffic for encryption. You restart SQL Server, and all connections to the database engine will be encrypted. Question, yes?
In this case, which you just described, where will the SQL look for a certificate? In the Windows storage certificates or SQL certificates?
So
Can you use TLS more than walk away from SSL in favor of TLS, which is storing certificates on the Windows?
So the question was, and I'm going to paraphrase, so if I didn't paraphrase everything, let me know. So the question was basically, where are the certificates going to be stored, and can we go get away from SSL and actually use TLS instead? So the answer is, on the Windows Store, they're going to be stored in the Certificate Management MMC plugin, because that's where SQL Server is getting them from. They're stored in the local machine MMC plugin. And can you use TLS instead of SSL? Yes, because as long as your cert is set up for TLS, then everything should just work fine. And so,
It would be that the sysops people have to maintain this storage.
yes.
If you use always configure option in the configuration manager, do you have to provide such certificate, or will the config manager take the certificate for the TLS?
So the question was, can you like just push this off on ops and just do everything through TLS, or do you have to actually put the cert on the machine? Did I paraphrase? So the cert has to get on the machine somehow, because SQL Server has to be able to see the actual cert, because the cert has to be there. You can do the management of the cert through a central management repository, like a key management system, or Key Vault or something like that. So you could, that way you could push it off to ops that way. I don't know if it's specifically going to allow you to do some of those things. I would need to look. It's been a little while since I've had to play with this stuff. But it should handle all the current versions of TLS and SSL. They should all be there as long as you can provide the appropriate cert to manage that. That should all be there. So this does require installing that cert and it being available on the actual Windows operating system itself. If you've got something like an always-on availability group or a failover cluster instance, you are going to have the same certificate on all the machines. So this is especially true of an FCI, because don't forget, within FCI, we're dealing with a single SQL Server instance and a single set of configurations. So we can't have different certs on different machines, because we're going to be using the fingerprint of the certificate by SQL Server to figure out what actual cert to use. So if we have a different certificate on each machine, those are going to have different thumbprints. And so that means that we're going to have an invalid configuration as soon as we fail over, and that basically is going to stop SQL Server from starting. So that is the one thing to be very careful of. So if you are flipping on this in a failover cluster environment, do a bunch of testing to make sure that you've got everything working on every single node in the environment, so that you don't have to worry about the instance going offline when all this happens. Question, yes?
If I've read through it right, the database certificate is encrypted by the master.
Mm-hmm.
The master is encrypted by the service certificate.
Correct.
So if you're putting a certificate on different machines, how does that work? Because obviously when you do the install on the different machines, you get a different service certificate.
So the question was, with the database certificates, those are signed by master certificates are signed by service certificate, and everything is installed on separate machines. How the hell does this all work? So the way this all works is extremely confusing. But the key point to remember is that the certificates in master that are signed by the service certificate, SQL stores 2 copies of those. One signed by the server certificate, one signed by your certificate. So that's the way that we can deal with this stuff. And so when any certificate stuff is done, unless you have like turned things off that you shouldn't have, or you've got stupid requirements that you need to meet, everything's going to be signed by both the machine and by whatever certificate you've given. So that way the system can start and then go grab that cert. You don't have to give it a root CA, but you just got to give it that certificate
from a root CA.
Yeah, a certificate from a root CA, yes. You don't want a self-signed certificate. So you would give it probably a certificate signed by your certificate authority inside your company, because that will be your internal CA. And then everything would be signed by that internally, as well as by the service certificates, or the service
So because it's been
passwords.
signed by the CA, it can be used on 2 different machines.
Yes, because it's signed by the CA, then you can use it on the 2 different machines.
Okay.
Yeah. Always protect your keys that you have within any SQL Server database, or really within any encryption process. Always keep those keys safe, and always rotate those keys on a relatively regular basis. The reason for that is because keys expire, or keys get compromised, DBAs leave. They might, once they've left, you no longer trust them. They may have the old keys. So when DBA leaves, we rotate keys, we need to rotate certificates. It sucks to have to do this, but it's the process, it's the thing we have to go through. So because of key rotation being an incredible pain in the butt, this is one of the reasons I always recommend to people, look hard at Always Encrypted. The reason I say that is because it's got key rotation built in, and Always Encrypted actually has room in it for 2 keys. The key you're using and the key you're about to use. Once it's done re-encrypting all the data with the new key, we can simply throw away the old key and pull the old key out of there, and we simply move that key that we're about to use into the key we're using position, and we still have that open position for another key, another thing to be sitting there. So there are ways to do key rotation. Without Always Encrypted, key rotation gets really, really hard. There's just no pleasant way of saying this, because we basically have to decrypt all the data and re-encrypt it with a new key, with a new cert. Yeah, so he's rubbing his forehead here if you're watching this from somewhere else. So it becomes an absolute nightmare for key rotation when you have to deal with these things, especially when you've got, I don't know, €500 million or €1 billion or a few billion euros. That just takes a while. So I've had to go to clients, and they've asked me about things. Go, yeah, life sucks. Sorry, we're going to have run this. We're going to have to build an app to do this flipping of re-encryption of data, and it may take 3 months to run. Oh, your audit requirement is that you need to have this done tomorrow? Yeah, you need to talk to your auditor and tell them you started the process, but it's going to take a while. Sorry.
You can't do schema changes and backups while you're decrypting and re-encrypting, can you?
Can you do schema changes or backups while you're re-encrypting, while you're dealing with this? Backups, yes. Schema changes?
I thought you had to pause it to do the backup and then.
Well, no, because you could do backups, while data's in flight. So you wouldn't, because all this is data change. So, it's pulling the data out, decrypting it in memory, re-encrypting it with the new value, and updating the row. So that's effectively just normal data change from a SQL Server perspective. So you can still do all your normal backups, while all this is happening. The trick is going to become backups are fine to restores. Where did I leave off? So you're going to need your app that's doing this decryption and re-encryption to actually record somewhere, where the hell am I in this process? Or the rows need to say which key is, encrypting the value. So that the app that's doing this encryption, decryption and re-encryption process knows where to restart in the event that you had to actually restore. Because backups are great until you have to restore, and then all hell breaks loose. So that's where things get really, really tricky is, cool, I've restored my database, now I need to finish my re-encryption process. My app doesn't support being restarted, so what do I do now? Or, and this is something you want to actually always build into that app that does that process, because there's this little thing every month that happens called Windows Update. And whatever server you're running that app on is probably going to patch. and it's probably going to restart. So it needs to be able to handle that as a graceful process of, oh, I've restarted, cool. I'm on row 8,000,003, and I'm just going to start from there and just keep on going. So there's lots of great ways to deal with that. And we could spend hours and hours, unfortunately, talking about various options and various caveats on how to make all that work. So there have been some absolutely colossal database failures out there. Obviously, Troy Hunt from down in Australia, he talks about them all the time, as he's got a lovely website that I hate receiving emails from called haveibeenpwned.com, which I would highly recommend if you're not signed up for it. You sign up for it. It's very depressing every time it emails you and says, hey, another site you've been using is compromised. And it's a small one like LinkedIn. What? How? So MySQL.com had a little bit of a database problem a few years ago. They'd like to brag, or they liked at the time, to brag that you basically couldn't encrypt, you couldn't do SQL injection against a MySQL database. And that was true unless you flipped a bit within the config file, which a little site called MySQL.com did. And then you can put multiple commands all in a single batch, as opposed to requiring only a single command per batch, which is a nice, safe way of doing it. So because they allowed multiple commands in a single batch, somebody found a place to do SQL injection on the MySQL.com site, and they dumped the entire user database table from MySQL.com and were able to do all sorts of lovely things with it. Next one. Little site might be owned by our corporate mama, Microsoft. Did anybody here work for Microsoft? Oh, good. Thank God. I meant to ask that earlier. Sorry. So LinkedIn.com, they've actually had a couple of data breaches at this point, and the passwords of somewhere between 6.5 to 115 million people have been leaked. Thankfully, the passwords back in the original breach, at least, were hashed and not salted. I believe they've changed their process to at least requiring salting now, but that requires you to change your password because they're hashed. They don't have access to your actual password to write it out there. Any single folks in the room, I'm terribly sorry, but your information has probably been leaked. Little company called eHarmony had a data breach as well. And that is all the ones that, if you want to take a picture of it, I saw a couple of phones up. All their passwords were accessed for a large portion of their user base. eHarmony went to the extreme of not having great passwords. Not only were they, not salted, but they were all stored in uppercase before they were stored, or before they were hashed. So that reduces the potential of the number of passwords you can have from a lot to a lot less. I have worked for companies that require this of their users, where the user can store a case-sensitive password, but on the back end it's actually stored as all uppercase. And I have immediately gone to the bosses and go, no, we're going to change this because this is stupid. Oh, but the users have problems. They can never remember the cases of their passwords. I don't care. Sorry, I'm a jerk. I just don't care. They're just going to have to deal with those. So I only have 1 minute left, so we're going to burn through these next things real fast, but these are just funny, not informational. So encryption myths, I've been told that all encryption is the same. Obviously, it is not. I've been told the SQL Server can't do encryption without third-party code. That is most definitely not true anymore. And it is true if you're talking about really, really old versions of SQL Server. So the only person that cares is him. Nobody else cares about this because nobody else is running these stupid old versions. Oh, he doesn't care either because they're old versions of SQL Server. You deserve to get your shit pwned. Oh, wait, I'm not supposed to cuss, am I? Oh, well. Hashing can't be broken. No, obviously it can. That's what dictionary hacks are for. Hashing hasn't changed since it was introduced. No, it changes all the time. Encryption hasn't been changed. Yes, it has. SQL Server can hash any value. No, it cannot. This is one of my pet peeves of the old encryption functions within SQL Server. This is not true of Always Encrypted. Give me a minute, Rob. This is not true of the Always Encrypted. This is true of the old functions built into SQL Server. You could only encrypt 8,000 byte questions. Rob, you have 3 seconds. Go.
Hash bytes can hash bigger stuff since I think 2016.
Okay, so this has been fixed in the newer versions, but so anything supported this has been fixed, but anything older it has not. So unfortunately, I am all out of time. Thank you very much for coming. Please do the survey. Thank you. Please make sure you do the survey and provide feedback to BITS. That's how they pick speakers for next year. If you liked the session, my name is Danny Cherry. If you didn't, there was nobody up here talking at all for the last hour. Thank you all very much.